UT Austin, Texas Austin. So he is the main advisor of Dr. Anamika. So if you don't know that, yeah, Dr. Santoso is a professor of the electrical and computer engineering at University of Texas at Austin, and holds electric engineering foundation Continental Teaching Fellowship in Electrical Engineering. His research and teaching interests lie in the broad area of the electric power transmission and distribution. He has written so many textbooks on different topics, so including he's a sole author of Fundamentals of Electric Power Quality, published 2010, and co-author of Electrical Power System Quality, third edition. That the third edition is 2012. He is also editor of the Handbook of Electrical Power Calculation, fourth edition in 2015, and a standard handbook for electrical engineers, that is 17th edition in 2018. He was the editor of the IEEE transaction on power system for 4 years. He became IEEE Fellow in 2015 for contribution to automated root cause analysis of electric power quality disturbance phenomenon. He has been on so many committees, including the past immediate chair of the IEEE PS Transaction and Distribution Committee and an IEEE Fellow. So with that, welcome, Dr. Santoso.
Thank you.
Get back to you.
Thank you so much for introducing me, and thank you everyone for attending this seminar, and for the opportunity also to speak to you about my work that is still going on. We speak a lot this morning to each one of you, and you know that my research that I spoke to you this morning is very different from what I'm going to show it to you. So this is going to be quite different. So today in here, I'm going to talk about the work that is currently going on, anomaly detection of capacitor banks with shorted elements. Okay, so the topic that I'm speaking about is the identification of health conditions of transmission capacitor banks. So as you can see, this is a typical transmission capacitor banks. You can see that when we say transmission capacitor bank, it is always meant to be like a three-phase banks. So you have like three individual capacitor banks. On the foreground in here, you can see this is one bank. So we can call it like phase A bank. And then behind it is another phase, maybe phase B bank. Okay, and behind it is the C phase bank, and so on. And the typical size of a capacitor bank like this, a three-phase capacitor bank, is probably between tens of megafarad to hundreds of megafarads. And then the voltage level is likely going to be 161 kV, 230 kV, 345 kV, or even 500 kV. And then they are widespread throughout the transmission systems. And as you know what they are for, right? I have seen that in transmission substation, typically they have one or more capacitor banks. And sometimes I have seen that more than 8 or 9 capacitor banks. So these are huge substations. Given that, a typical utility operator, transmission operator, they may have hundreds of capacitor banks they have to operate in the systems. Okay, and then you can see from here that each individual banks is in fact made out of multiple capacitor units that are arranged in series and arranged in parallels. So it means that for the entire capacitor fleet, they can actually have tens of thousands of capacitor units. And unfortunately, many of these units have undetected shorted elements. Okay, so what are the impacts of these shorted elements? Sometimes they cause nuisance tripping. Okay, and we'll be talking about that. And then the worst case of this nuisance tripping, if the tripping did not happen for any reason, it may eventually snowball and leads to a short circuit event leading to a full-blown catastrophic failure that eventually destroyed the entire capacitor bank right there. So based on that, the objective of this work is essentially to develop an exploratory machine learning tool to identify the health status of capacitor bank. And then what we want to do here is to classify it as normal health condition or abnormal health condition. Okay, so this is a very common engineering problem in anomaly detections. You can find it in many engineering issues, right? So when we say abnormal in here, it means that you have shorted elements within the capacitor bank, within these three-phase capacitor banks. That is abnormal. We don't want that. We want to detect that. Okay, and then normal, it means that it is absence of shorted elements. Okay, so that's pretty straightforward. We want to identify whether the capacitor bank has shorted elements or does not have shorted elements. Okay, so here the diagnostic modality is power quality monitoring data. We want to use three-phase voltage and current measurement from power quality monitoring data. Of course, you can use other data, for example, like infrared imaging or anything else. But here we focus on using power quality data. Okay, so I have told you about the background and the motivations and the objectives. So now I think it is time to tell you about the flow of this talk. Okay, so first I'm going to show you the data source, where the data sources are coming from, because I think this is going to be very important when we want to design a machine learning tools to solve this anomaly detection problem. And then I believe that we need to know about the capacitor design, how the capacitor is designed, and what the failure mechanism is, and what are the aftermath or the consequence of the failures, right? Because we are power engineers, we are not just going to design our machine learning without knowing the background. Okay, so given this information here or the background knowledge, what we want to do now, having know this data source and capacitor design here, we want to design a machine learning models. And then there are two competing models. This is a very common process, whether we want to design it based on single stage detections or multi-stage detections. So as you can see here, I'm going to settle with two-stage detection models, okay, which I will explain to you later. But what I want to emphasize here is the selection of the feature factors, okay, and the testing data, as well as the performance. I'm not going to talk much about the learning algorithm itself, or how you train the algorithm, or how you set up the tuning parameters. I'm not going to talk any of those things, okay, because the machine learning models that I'm using are very, very simple and very established already. So I'm going to use just these KNN models and also the support factor machine models, very established already. And then finally, I'm going to talk about the transferability of the model, meaning that the model that I developed based on data coming from one particular substation, can these models be used for data that are captured from other substations? So we want to investigate about that. So that is approximately the flow. So now let me go back to the data source. So again, in here, what is our objective? Okay, we are given a set of power quality monitoring data, okay, which I have not shown you what they look like. Okay, but then from each monitoring data, event data, we want to say whether that data or that waveform is associated with this health condition of the capacitor bank, or the other health condition of capacitor, normal or abnormal. So where are the data coming from? Well, you can see that the data would be coming from here. Okay, so this is a typical layout of a transmission substation. You have a main bus, okay? You have a main bus in here, and coming down from the main bus here, you have a capacitor bus, okay? And this capacitor bus, essentially, you can see it hosts 4 capacitor banks. So this is a one-line diagram, meaning that this if this is for the A phase, B phase, and C phase looks just the same. So it's a one-line diagram in here. And then you can see that we have a capacitor bank right here. This is one bank, this is bank 2, bank 3, and this is bank 4. They are all identical in here. Now we have a circuit switcher in here. The purpose of this circuit switcher is to energize a capacitor bank in and out. Okay, but this circuit switcher here has a pre-insertion inductor, okay, to reduce the inrush current. And then we have a circuit breaker right here, and the purpose of the circuit breaker is to interrupt fault currents. And then our power quality monitor is actually located right here and there. Okay, so we have the voltage is measured at the main bus, and then the current is measured at this capacitor breaker, capacitor bank circuit breaker right there. Okay, so our data source is not coming from here or there. If we have power quality monitor located in here, that would be much easier to develop our machine learning models. Instead, our power quality monitor is here. So this current that is measured in here will see all the currents together, right? You see the issue in here. So our voltage and current waveforms that we will be using for doing these anomaly detections come from here and not from here. Okay. Now, incidentally, also that in some substation they have power quality monitor installed at the load side of the circuit breaker. Okay, and then they also have these 87 relays, the differential protection relays. We don't use any of this data. If we could use any of this data, our development of machine learning would be a lot simpler and probably a lot more accurate. Okay, but the reason that we don't want to use this because we want to use an independent data source that are not related to the protection data source, and then only using this data source from here to perform our anomaly detection. You guys are following still? Okay. So now, so that is the data source where we got the data. Now I'm going to explain to you what it looks like, the design of the capacitor bank. So this is a one-line diagram, but here this is a three-line diagram, meaning that here you will see phase A, the A phase, B phase, and C phase right there. And then you can see that in here, so here you have, this is the A phase bank. It is made up of two parallel strings. Okay, and in each parallel string, you can find 5 capacitor units that are connected in series. Okay, so here this is a 3-phase bank, and then this is individual bank in here. A, B, and C, they are all identical. And then inside each individual bank, you have these capacitor units. And each capacitor unit is rated 600 kVAR. And by the way, the entire 3-phase bank is 18 megaVAR. But in here, each one of these is just 600 kVAR at 19.1 kV. Okay, and then in real world, it looks like this. You have seen some of this maybe in the past, right? Okay, but inside here, it is made up of capacitor elements that are arranged in series and parallel. Okay, that looks like this. Okay, so this is what we call the series group. So you have 10 series group, and then each series group is made up of 3 parallel elements. Okay, 3 parallel elements that are arranged in parallel. Now, what is capacitor elements? Well, capacitor elements are very simple. Okay, you can even build it on your own, although the quality might not be as good, right? Okay, so essentially you have aluminum foils. Okay, and then in between you put your dielectric film, and then you roll up. Okay, looks like a cigar, and that is your capacitor element. Okay, and then you arrange them. Okay, but the key thing in here is that you want to have each element to be exactly identical, and that is manufacturingly very difficult to do. But that's the idea. You want to have them exactly uniform. Now what happens if there is a breakdown here of the dielectric? So remember that the dielectric is in between the foil. If you have a dielectric breakdown, it means that the 2 foils are going to weld. Okay, and they form a stable weld. So it means that the impedance is going to be 0, right? Because it's a fault. So you can see that if one capacitor element fails, it will take the entire group in here. Okay, so in this case, we are talking about fuseless capacitor bank design. There is another group of capacitor bank that are fused capacitor bank. But fused capacitor bank are very old technology. This is relatively new. Maybe new in the sense that maybe it is 30, 40 years already. Okay, so this is fuseless capacitor bank. This is what I'm talking about. For fuseless capacitor bank, when they fail shorted. Okay, where for the fused capacitor bank, when they fail open. So whatever I do for this machine learning development for this fuseless capacitor bank will not be applicable to fused capacitor bank. You have to design a different machine learning because the failure mechanism is not the same. Okay, so suppose that one fail, it takes out the entire series group, and as a result of this in here, the next group or any group in here will experience higher stress voltage in between. That will then cause the dielectric to break down even faster, accelerated breakdown. So at the end, you may have multiple capacitor units, okay, that have shorted elements. So, so eventually, what happened is that, so this is now we need to understand about the consequence of shorted elements. So what are the consequences of shorted elements in here? Okay, remember that in here, you can see there are relay circuits, and these are 87 relay, meaning that they are differential protection relay. For this particular case, usually we use a voltage differential protection that try to measure the differential voltage. And if the capacitor is healthy, there is no shorted element, the differential voltage is 0, because there is a K factor that you can adjust such that the differential voltage is 0. Now, in a situation like this, if you only have several elements that are failing, okay, that are shorted, and the differential voltage has not reached its threshold, the capacitor are just going to operate as usual. Nothing happens, just operate, okay? So that is the first possibility. And the second possibility is that if some elements already fail, and then you have additional element continue to fail, and then such that the differential voltage now is above the threshold, the one of these relay is going to send a trip signal to the circuit switcher, and then the circuit switcher will open, and then that will create what we call nuisance tripping, okay, or involuntary de-energizing. Okay, so this is the waveform that you see. So this one in here, this is the consequence number 2, that that the circuit breaker is trip offline, is forced to trip. Okay, so this is nuisance tripping. You can see this is the voltage that is normalized to 1 per unit, whereas this is the current in actual units. Okay, so this is the power quality monitor data, and that one over there is a capacitor. It's a voltage measurement and the current measurement as well. You can see that the capacitor did not trip; it's just operate. Now, you can see. So back to our objective. What is our objective? Given these waveforms to the machine learning models, okay, tell us whether the capacitor is healthy or unhealthy, whether it has shorted elements or it's free from shorted elements. Okay, but when you see these waveforms, it looks just like any capacitor de-energizing, normal capacitor de-energizing. Well, capacitor is energized and de-energized, right? According to some prescription. You look at this, it looks just like normal de-energizing, scheduled de-energizing. Okay, so how can you tell that this is there are shorted elements or not? Okay, you still follow me? Okay, now, so these are the 2 consequences. Now, how do we begin now? If we are given a bunch of data such as this, okay, and how do we begin to design our machine learning models? Okay, first, of course, we need to have data from the field report, right, to tell whether actually this capacitor has shorted elements or that capacitor doesn't have shorted elements. So we are fortunate that we are provided with the actual field report, not just the raw data, but we are also given this data. So I have to sanitize so that to protect the owner of the data. So here, this is the time, the date and time. This is which power quality monitor. This is which bank that has the shorted elements, and then this is the capacitor bank design. And then eventually it tells you that based on the field analysis, okay, there are 5 shorted elements in the A phase, okay, or there are 4 to 5 shorted elements on C phase and 1 to 2 shorted elements on A phase, like that. So, so again, what are the data that we have? We have the power quality monitoring data, and we have this set of data. So in other words, we have the raw data, and then we couple that with the label. And these are the label. These waveforms in here, okay, has abnormal elements. We don't necessarily need to know how many, as long as we know that in the capacitor bank, there are shorted elements. Whereas this one, there are shorted elements too, right? And maybe in some other waveform, there is no shorted elements, like that. Now, given that, it becomes like when the time comes, we have to design the machine learning. We have always two competing ideas, right? So we can design with a single stage. It looks just like this, very attractive, in fact, where we can have the raw time series or feature factors. We have not decided. Maybe if our machine learning tools are very powerful, we can just take the raw waveform and dump it into it, okay? And then pair it with the label. Pair it with the label right here, okay? And let the TensorFlow or whatever that you use and come up with the best tuning model, okay? Parameters, and then you adjust, and voila, you got your results back, okay? And that is fine, okay? But then what do we lose? Okay, what do we lose in here is that we surrender our intellectual capacity to the machine learning tools, that we actually don't know what's doing. And usually when we apply this to the real world situation, users tend to dismiss this sort of approach, because why? There's no influence in guiding the course of the decision. And then there's no feasibility or transparency to the process, right? And users may have hard time trusting the results at all because they don't know what's going on. So this is like a completely unknown systems that they have to accept the results. And then the worst case is that usually when the results coming out say it has an abnormal elements, but when being asked a question, why do you think that there is an abnormal elements or shorted elements, cannot provide the answer, right? Okay, so what we do is that we try to inject our knowledge background to it, okay? Because we are power engineers, we know what's going on, so we want to influence the decision-making process in here. So what we decided is that we want to have a multi-stage. 2 stages is enough in this case, okay? The first stage is really just receiving the waveforms, okay? And we don't know yet whether we are going to use raw data or feature factors at this point, but we will just have one machine learning tools in here that will help us determine the effect of the shorted elements. Because if the effect of that shorted elements actually results in tripping offline, it will go to this next machine learning modules. If that event does not result in any nuisance tripping, it will go to this one, and then it will from here it will determine whether the event is normal or abnormal, like that. Okay, so so in other words, if this is the waveform that you see here, that is on top of this, it will pass down to here, and then the question become whether this waveform is caused by a involuntary tripping or non-involuntary tripping. That will be very difficult. Okay, so in here we will see that in the next one in here, because the split in here is essentially equivalent to saying that is there any switching operation or not? Okay, because in this de-energizing operation, it could be voluntary, it could be involuntary as well. So we want to split it in here and decide. Okay, so from here, so the purpose of this model in here is then becomes very simple, that we want to identify the switching operation of that event. Okay, now So how many switching operation is possible in this case? Okay, by looking at the waveforms, okay, there are 6 possible operation type. Okay, now let me show you. So this is one operation type in here. So this is like no switching operations. You can see that from here. This is the voltage waveforms, and this is the current waveform. This current waveform is 0. So what does it mean? This current 0 being 0. Do you think there is any capacitor bank in operation in the substation? So this is the voltage measured at the main bus. This is the current that is measured at the capacitor bank bus. Okay, the circuit breaker, and it's 0. It means that there is no capacitor in operation, right? So in here, how about in here? So this is the voltage, and this is the current. There are current in here. The same amount of current also appear in here. So there is no energizing in here because the number of capacitor bank that is on operation in here and in here, they are the same. There's no operations. But could there be shorted elements in here? Could there be shorted element in here? Yes, there could be. So shorted element can appear in this switching operation, which is no switching operation. But can shorted element appear in here? It cannot appear in here because there is no capacitor bank to analyze, right? So you have a possibility of shorted elements in this waveform in here, right? Okay. Now, how about in here? This is a class of de-energizing. Okay. Again, voltage and current. Okay. In here, initially you have current. Okay. So this current, you have that in here, and then after that, it's de-energized. Current becomes 0. So essentially, you have one capacitor in operation, in surface, and then it's de-energized. Okay. Whereas in here, you have one capacitor, you have one or more n plus 1 in here in operation, and then n in operation in here. So 1 is de-energized. But then the question is always that, can you have shorted elements in here? Yes, you can. So is this normal de-energizing or nuisance tripping? We don't know. It could be, right? Could be nuisance, could be part of the scheduled de-energizing. We don't know. But nonetheless, shorted elements can appear here, can appear in here too. Okay. Now, this is another class. This is the class for energizing. So initially you have current 0, and then you have current in here. Can shorted element appear in here? Yes, of course, there could be shorted elements already. And then once it's energized, it's still operation, right? Likewise in here. So shorted elements can appear in here and also in here. So again now, essentially, for this first stage, our question now is to become like, what are the switching operations of this event here? Is this energizing or de-energizing or not switching? Okay, so what would be the best way to figure out that switching operations? Of course, we can use voltage, or you can use current, or use voltage and use current, right? So which one is the simplest one? If we are using the voltage alone, okay, voltage doesn't provide much information. Although every time a capacitor is energized or de-energized, you have a voltage difference of about 1% or 2% at most, like that. But the most useful is just using current. Of course, you can calculate the reactive power, but that is going to be even more complicated, right? So we just use current in here to measure, try to identify whether there are operation or non-operation, switching operation or not in here. Okay, so so here the feature factors that we choose is RMS current at the beginning and at the end. Okay, so we only need to calculate 4 cycles at the beginning and 4 cycles at the end. Now, in here, what I want to show you in here is really that the selection of the feature factors are very important. We want to select feature factors that are related to the real world conditions. Okay, and that practicing engineers can understand and relate to. If we choose some abstract feature factors that you calculate from some mathematical process, it may be not related to the real world condition, and that would create some issues when you try to explain it to in the applications. So in this case here, we use the current, which is very simple. And now here, you see that I only use data from 2 months of measurement from this substation with the pseudonym of Tarzan in here. And then typically it is like 32.5 cycle long, like what you have seen. Okay? And then this 281 event consists of like 50 events of no switching operation, 88 events with energizing or de-energizing, and then 143 event of energizing. And then we plot the feature space. The plot of the feature space are very critical also to the users, because when they see the feature space, they want it to be something that they can understand, relatable. So you can see that the feature space that I have in here is the RMS at the initial recording, and then RMS at the end of the recording. Now, if you look at this point in here, so initial is 0, and at the end is 0. So what does it mean, 0 and 0? It means that there is no capacitor being analyzed. Now, if you look at this one in here, this is minus 102, and this is, this is minus 102. The current is 63 amps. This is like 63 amps in here, initially 63 amps, and then at the end it is 63 amps also. So it means there is no switching operation, right? So you can see that those that has no switching operation, they line up in this slope. Okay, so you can immediately see it. And then this one is de-energizing. So de-energizing is like initially you have some values, 63 amps, and then at the end you have 0. So from 1 capacitor bank to 0. In here you have like 126, and here you have 63. So from 2 bank to 1 bank. So this line here has to do with de-energizing operation. Now the next question is that in each of these dots, which represent a switching operation, is that switching operation nuisance tripping or scheduled tripping? That's what we want to know. Okay, you follow? So we go into stages in here so that we can intervene, and then maybe at the same time pull out any information that could be useful. Okay, now you can see that this is energizing operation. Now this chart is, I think, is very useful because all of this number here are kind of like a discretized, because when you have a capacitor bank that is in surface, the voltage, the current is maybe 63, 65 amps or so on, 130 amps. So there is a range to it there. Now, so that is this training data. And then for this training data in here, we use a KNN model to train. And then with 2 months of data, testing it, we use 54 months of data. Okay, so, or no, we use 8 months of data in this case. So, and then it's a perfect classification of 100%. And this is 16 months of data is also perfect accuracy. Okay, but that's not really the point. The point is that in doing this work, the most critical part is choosing the feature factors. Once you understand the feature factors that are effective, your model is going to be very simple. You don't have to use a very complicated machine learning models. And besides, when you look at these results in here, you can actually tell whether the capacitor bank may have issue or may have, or the system have an issue. If you think about like let's say for this one here, okay, this one here, current is roughly about 65 amps, right? And current about here is roughly 65 amps. But you see there are some currents in here and some currents in here. So that is not supposed to be happening, right? Supposed to be, if in the ideal case, it's supposed to be a perfect single dot, but it's spread out in here, it's clustered in here. So this is probably representing some good capacitors, whereas here there might be something happening in here, right? Okay, so like this one too, it's not like forming a tight cluster. Now, so that is the first part, okay, the first stage. Any comments or questions up to this point? All right, So the next part now, okay, is that going deeper now, okay? So again, we start with this waveform, for example. Waveform, pass it through this stage one in here. And then the next one in here is that, oh, this is a switching operation. Pass it through here, switching operation in here. And then the question next, is it normal? Is it abnormal? Okay. Now, if this is a different waveforms, suppose this is like a no switching operation, it will pass through here because the feature factors that is used to detect normal or abnormal for one with switching or one without switching are not the same. Okay. So now we are moving into this part here. Now, now you see these are the typical waveforms. Okay, these are the voltage waveforms. Okay, on the top, these are the current waveforms. This is energy de-energizing. They look just like normal de-energizing. You wouldn't know whether this is there is a shorted elements or not inside it, right? So what are the feature factors that we should use to tell whether there are shorted elements or not? Very common, right? When you think about short circuit, what do you think? Impedance is lower, right? I mean, in ideal case, if it's a voltage fault, impedance is 0. But regardless, impedance of that equipment must be going down, right? Okay, so, well, that is what we choose. So there are two competing feature factors, impedance predictor or phase current, okay? So you see this is the waveforms in here. We calculate the impedance. Calculating impedance are not going to be difficult. Okay? It's simply that you choose voltage divided by the current and make sure that if the current is 0, you don't do any division operator because then it will create a NAN. Okay, so I just put NA here. So you see in here, so these are the impedances, okay, for A phase, B phase, and C phase, like that. Okay, and then what do you see in here? That they are all above the threshold. So again, I have to compare it with the rated value of the impedance. Okay, taking into account of some tolerance, and the manufacturer's tolerance is 6% in here. So, but you see that all of the impedances are above the threshold. So what does it mean? Are there shorted elements? Do you think? There are no shorted elements. If there are shorted elements, where are the impedance should be? It should be below the threshold, right? So it means here there are no shorted elements. But what does the field report tells us? It tells us there are 6 shorted elements on B phase. On this phase, this is the B phase, 6 shorted elements. So it means that they don't match. So my predictors may not be as good. This impedance predictor. That's quite perplexing, isn't it? Right? Okay, it can stuck for months and maybe months and months, right? Figure out why this doesn't work. Okay, that's about what happened. Okay, I don't get stuck months, but I get stuck for a few days. Okay, and then eventually I abandoned that. Okay, I thought that my impedance calculation was incorrect, tolerance was incorrect, or anything, right? And then I sorted to using, how about just use current? Okay, current predictor. Okay, current predictors, okay, can just calculate the RMS current for the entire waveforms. It looks like this, coming down like that. Okay, and then I calculate the before the energizing and after the energizing. And look at the current, tell us, okay, current B is above the threshold. Current A and C are below the threshold. And they match what this one says in here. Okay, and then the post switching RMS, they are all very small number. They are, after a while, they should go to 0, right? Okay, but this is just decaying slowly in here. So the feature factors that I choose was based on current predictor, which is essentially the amount of current above the threshold and the time in which they are above the threshold. Okay, so there are delta I hat, delta current for the head, and delta current for the tail portion and the time. Okay, and with this, it works 100% of the time. That's what. Okay, But now going back to the impedance, why it doesn't work? Because that's what we need to know, right? Why it doesn't work? Well, it doesn't work. Does anybody wants to try? It doesn't work because of this, where our measurement is taken. Our measurement is taken right here. Okay, if our measurement is taken right here, we probably have a better accuracy in calculating the impedance, because the impedance that we calculate would be just impedance that is looking down in here. And then if we know the inductance of the pre-insertion switch, then we can actually calculate the impedance of each of these. But what we have is that the measurement is just coming from here, right? And then it includes all impedances from all other equipments, okay, that mess things up. Okay, so that takes a while to figure out. Now, so eventually, what I want to say is that we settle down in this feature predictors in here, the predictors there. Okay, and then again here, we use the data from Terson substation. This is 161 kV, 18 megawatt capacitor banks. Okay, we only use 8 months of data. Okay, and we use these 4 predictors in here, and then we train it using SVM model. Okay, and then supposedly, if we want to, we plot the 4-dimensional space. But there's no way we do that, right? So I only plot this one, these two, feature space in this delta I hat and delta I trail. And it looks like this. Does it have any meaning, relation to the real world? Okay, apparently it does. That's why I plot it. Okay, otherwise I would not plot it, right? So what is the relation? This is the current that is above the threshold at the beginning. Okay, now if the current is below the threshold, what does it mean? There is no shorted element, right? If the current at the end is below the threshold, what does it mean? There's no shorted elements. Therefore, the shorted element must appear in this quadrant only. Okay, and in all other quadrant in here, that would be for capacitor with shorted elements. It means that either the measurement has the current that is above the threshold at the beginning or at the end, or both, right? So from here, you can tell very quickly that where the shorted elements are. They are not here, but they are outside. Okay, and from here too, you can tell where most likely errors are going to be made. Errors are going to be made most likely when they are overlapping, the hyperplane overlapping, right here, in this case, right? So with that, okay, with 8 months of training data, okay, I use MATLAB, okay, training data. We tested with 54 months of testing. So this is a typical, very non-typical way of doing, right? Typically, you have 80% of your data for training, 20% of your data for testing. No, we don't do that. This is a real world problem. We use only 8 months and then the other 54 months for testing, because we want to really robustly test it. And look at this, okay? So this is data set 1, 2, and until maybe 10 in here. We have 10,000 objects here. And then out of these 10,000 objects, 2,000 of them have shorted elements. Okay, so it's about 19.58% of it has shorted elements. And then in here, this is using SVM, and this is using KNN. You can see using SVM, the error rate, I mean, there are only 4 instances, 4 objects where it makes mistakes. And this one is 2. Okay, when you look at this, you will declare, wow, SVM performs better than KNN. No. It's just they perform the same. I mean, the difference between 4 and 2 is not making a big deal, right? Okay, so this one is only making mistake. Error rate is 0.2%. Okay, this is quite remarkable. But aside from the number, is that I think from each identification, we can explain why the result is like this, why it is not like that. Okay, because we can always go back to the chain and figure out what are the feature factors and where they are located. You can even actually going back to each one of them and then say, oh, this is the event. Click that. And then it will show what are the factors. Okay, predictors that are helpful to doing that. Okay, so that is that part. Okay. Now, for this part here, this is the part that is a lot more difficult to do. Okay, because first we don't have much data. Okay, because this is, and also this is probably not very critical. And the reason being that the capacitor bank still in operations. So we just let them continue in operation. And then maybe at the end, we will detect it when it creates nuisance tripping. So we can let that. But we proceed anyway. The predictors that I use, that 4 predictors are not going to be enough. I have to expand the predictors. The current base predictor alone is not enough. I have to use a voltage-based predictor as well. Then these are the typical waveforms, okay? You can see that this is almost like a textbook example case where the shorted elements is not, or maybe only a few in here, and then suddenly it happens right here. You can see there are distortion in here. Whereas in here, you can see the bank continue to operate. And then you can see that it looks like there's nothing happened. Actually, there is a self-shorted element. And then you can see there are events like this, okay, recorded in the monitors, okay, that has nothing to do with capacitor banks, okay. And so there are many diversity to this waveform in here. So, and like this too, okay, maybe have to do with a voltage sag upstream somewhere, right? And then here, so this is, again, we expand the feature space, but it doesn't really work very well because the error rate here is about 10%, okay? And it may be good still, but then given that this many uncertainty, it is probably not going to be too useful. Besides, the capacitor is still in operation, okay? So that is that case. Now, finally, a few comments on transferability, right? So in real world applications, what we want to figure out is that can the model that I developed based on data coming from one substation, can I transfer it and use it for data coming from other substation? Can we do that? Okay. Otherwise, we would have to rebuild our model for different data sets, right? Okay. So in order to do this, we have to at least build another model. Okay. So the previous one that was built is using Carter test data. Okay. And then now the new one that was built is using Carter data. And they are all have the same capacitor units, same construction, but different size. One is 81 megafarad for Carter, and the other one is 18 megafarad for Tarzan. Okay. And the way that we test it is like this. Okay. So suppose that this is a Carter train model, and this is a Tarzan train model. We use a Carter data to test. So from here, passing down to here. So what is our expectation? That it should work, right? Because it used the same, it's coming from the same parent, okay, basically. It's coming from the same data sets, right? The same substation. But then when we test it to Tarzan now, so the question becomes like, can Tarzan train model perform as well as Carter train models when tested with Carter data? And likewise with this one. Yeah. So this is the reference case, and this is the reference case. Okay, we will declare transferability is successful when the performance are about the same, right? Okay, now, but first, I want to show you the feature space. One is with Carter, and the other one with Tarzan. Yeah, immediately you see the difference. Okay, well, immediately we see the similarity first. Okay, in that here, this is all the normal element, and outside it is all the abnormal elements, right? Abnormal capacitor condition. But then you see that the numbers here is 6, whereas the number here is 3, and this is 8, and that is 5 in here. Okay, and you can see that too. This is 12. So from here, you probably can guess that the hyperplane formed by this Carter train model are a lot bigger than the hyperplane formed by this Tarzan, right? Okay, and why is that? Because the Carter capacitor bank is 81 megafarad, whereas Tarzan is only 18. Okay, now, so this is the testing. Now look at these results. So this is the Carter train model, okay, tested using Carter data reference case. Error is only 2 instances, which is reasonable. But when the same test data, Carter data, tested on Tarzan train model, you can see it makes all the mistakes. So when we think about this, you can liken this like a funnel, okay? That the Carter funnel is pretty big, okay, whereas Tarzan is pretty small. So all the features factors coming on this side is spilling over. Okay. Now, same with this one. So I tested with one data that is from July to December 2020. This is from January to June 2021. Basically, it's a whole year of data. You can see. So conclusion from here is that Tarzan data cannot be used to analyze Carter data. Okay. Now, this is another one. Okay, now we have Tarzan data tested on Tarzan train model reference, which is that one, perfect. Whereas now tested on Carter data, Carter train model, you can see that it made some mistakes in here, but it's reasonable. So from here, we can say that Carter data is transferable to Tarzan. Okay, likewise in here. So that is one of the validation. But that's not the end of it. The actual question is that how do we improve transferability? Okay. So clearly, you see this one. Maybe one technique to improve transferability is what? Normalize the current. Could be, right? Normalize the current. But how would you normalize the current when your actual number of capacitor banks are not the same? Are you going to normalize it to one capacitor bank in surface, or how? Okay, so that is some of the discussion that is going on. And also, what else can we do to promote transferability? Should we use multiple data sets from different substations? Okay, but in doing so, are we going to lose resolution or precision on that? That could be, right? So there are always pros and cons in doing that. And we have not done that at all. So, but that is the transferability issues, which I think is very practical. But again, maybe it is easier just simply to take data from the substation and use it for the substation and forget transferability. Could be, right? And then it should perform as good. But okay. So in closing comments in here, to me, when we develop this, we want to use all the background that we have, background knowledge, okay, in order to design a meaningful machine learning that is probably relatable to the real world conditions, so that we can incorporate our domain expertise and the model. Okay, you can see the model that I use are simple. Okay, and then we can figuring out, most important also I think is figuring out the feature factors that you can tell the story about to the practicing engineers, right? Improve transferability and transparency, and of course later on probably transferability are going to play some role also. But I think if you have enough manpower or you automate all of your training methods, then it's probably okay not to do transferability tasks in here. Okay, so that's what I have. Hopefully it reinforces your interest in applying machine learning, and don't just throw your imagination to TensorFlow and ask TensorFlow to solve for you. Okay, all right.
Okay, thank you. So that was very
Yeah, thank you.
Maybe let's first go to the people online. So anybody has question? If so, please unmute yourself and ask your question. No? Okay, so then people in the room. Good, first. Yeah.
So, a quick comment. On slide 6 and like you showed the de-energization and energization. The rate of change of current was same. Is it because the capacitors are identical?
What slide number did you say?
Probably 60. Figure where you show the slope.
Ah, okay. This one, right?
Yes.
Okay. So in here, yeah, de-energizing and energizing, the slope is the same because the capacitor size is a discrete. So one bank at a time. They don't energize two banks at the same time because it's always like, even, I mean, this is a three-phase capacitor bank, right? And each phase has its own circuit switcher, and they are gang operated, meaning that if one phase energizes, all phases energize like that. But there is always like a time difference, maybe a few cycles, but never exactly the same. But at the end, this is what you see, like that.
So would the slope be different for different size capacitors?
Probably. So in here, the discretized current, the quantized current is 65 amps, give or take. But for a different size, that would be a different quanta, right? And then, yeah, it could be. But I think in all of them, they should be still having the same slope. Okay, that's. But I think this is a very good representation to know how your capacitor banks perform over time. Okay. Yeah.
I have a question regarding slide number 19.
19?
Yeah, 19.
Okay.
So here, yeah, you talked about the feature that you use, the current, right? So what current is this? Is this just RMS current? Or?
Yes. So this is the instantaneous current. And from there, you calculate the RMS current. So this is RMS current.
So what is the threshold that you use for this, for the current?
Oh, 6%. So you know the rated voltage of each capacitor unit, right? And then you know how it is arranged in series and parallel. And based on that, you can calculate the total current that is supposed to be flowing, rated current. And then with the rated current, you include the manufacturer tolerance. And then that would be your so-called rated current. Okay.
So you are using the same impedance data that didn't work, but it works. Okay.
Yeah, like that. So this is just one way. Okay, a different way of selecting feature factors. You can actually use the differential voltage if you want. Okay, but when you use differential voltage, you have to use the 87 relays to give you that number. Okay. Now, this whole problem would have been much easier, okay, if you have access to relay data, okay? Because actually, when you really think about this, a relay, okay, is used to trip the circuit switcher, right? Okay, and then you can always go back to the relay. Why this relay trips? Is this a nuisance tripping, or this is a prescribed tripping, right? And based on that, you can tell. Okay, but the problem is what? Some of the catastrophic failures that happened in the past, it is because the relay failed to trip. Okay, so if you use that one, then you're probably going to miss some other things. So that's why you have to use this one separately. Okay, and this relay are 287, 387, or 487 relays. Okay, so you can see that in this relay, you need to have this resistance in here. And then you need to have this capacitor. And this is also a capacitor. And what happens if this capacitor fails? The relay fails too, right? So that was the issues, okay? Why we want to use independent data to do this abnormal switching. But maybe in the future, okay, I'm thinking that you could actually use your power quality monitor and then your relay data and merge them together, okay? And that would be even more powerful. Your accuracy rate, I think, would be really good, unless your relay fails. Then you have to rely on the power quality monitor alone, okay? But that was the idea, okay?
Thank you.
Any other questions? Okay.
So at the end of the seminar, you were talking about how we could make the data transferable between substations. And we were talking about normalizing the current or normalizing your feature vectors. Have you looked at consider different ways of machine learning that can generalize better? So things like ensemble learning.
Oh, yeah.
Because those are apply quickly. So I was wondering if you did any of those testing.
I don't do any of those.
Okay.
Because yes,
Yeah.
those are those machine learning techniques that you can use to improve your transferability. My interest is looking at it from the power system side. Okay, but yeah, of course, those things can be done. Yeah, you can have ensembles, which is very good to do. Yeah.
Or even just pooling all of the data together
Yes.
in one puddle and
Yes.
Okay.
Yes. But the question is that the voltage could be different. Some but there could be multiple data sets. You can form a pool from 161 kV data sets, 345 and 545, right? 345 and 500 kV, like that. But I think normalizing the voltage is very common. Normalizing current are not typically common to me. Okay, yeah. From the engineering perspective, like when we talk about fault current, we don't normalize fault current. We can say however many Ka, that's it, but we don't say how many per units, right? Okay.
Sorry, one last question. And so when you use machine learning, you want to keep the electrical engineering aspect by designing the feature vector well. So that's where you're applying domain knowledge to the machine learning.
Yes, that is you got the main message. That is that. Otherwise, you can see this is all about KNN and SVM. Very simple, right? That.
Maybe last question. Lucky person to ask the last question. Where do you want to go? Okay. So
All right. Okay.
we really appreciate that. That was very informative time. So maybe one more round of applause. Thank you. Yeah. So can stop now.